we are still in module 5 that concerns extraction of metals from oxide sources. Now, we have discussed in good bit of detail extraction of aluminum from bauxite, and earlier to that we have discussed extraction of magnesium from dolomite. Now, there are many other metals which come from oxide sources, and these oxidic minerals may not be as rich as say in the case of bauxite, where we find bauxite very rich in aluminum in nature. Of course, you have to take out the topsoil and then you have to mine from bauxite. One can get dolomite also, good quality dolomite, good quality magnesite, without too much of other gang associated. But there are many other oxides which are not found as ores or minerals very rich in them, but we can obtain the oxide concentrates by various mineral dressing techniques. Let us discuss one metal, that is tin, which has very wide application and very commonly known. Unfortunately, the word tin has come to refer to cans only because they are coated by the tin metal. They are not made of tin, they are iron cans coated with tin, but that makes the use of the word tin very common. Not many of you may know that tin is used in a surprising variety of applications. Unfortunately, India is not one country which produces much of tin, because we do not have tin ores, but India has to consume tin because we need tin. The tin has to be imported. So, let me start discussions on tin by looking at the various applications of tin. Unfortunately, slide I am going to show you has too much of written material. Try to see what is there, or else I will help you by reading things out. Why is tin an attractive metal? If I say it is attractive because of various applications, that is not the right thing to say. Actually, the various applications come because it has many attractive mechanical and chemical properties. Because we have these attractive properties, we have found applications. The attractive properties comprise mechanical properties. It is malleable, it is ductile, which means a piece of tin can be made into a thin strip, it can be formed into many shapes. It is also very useful in making different kinds of alloys which find wide applications, and you find tin or tin alloys in many household consumer items like collapsible tubes, foils, etc., etc. One big advantage of tin is its melting point is very low, only 232 degrees, and if it is low, it can find applications in where we need some low melting alloys, like in solders for joining wires. So, it is used in solders. It has a remarkable resistance to corrosion, and it is also resistant to toxicity, and that is why tin cans coated with tin can be used to keep beverages, food items, liquids, and they will not be spoilt. So, you see the applications. Now, look at them in a little more detail. We can think of applications in 4 categories as metal. Now, as metal, it can be used through extrusion in making collapsible tubes. As powder, it is used in many decorative purposes. It can be rolled, made into foils for wrapping paper. These are uses as metal. More important are in the form of alloys. I have listed some. Alloys to make art objects, white metal bearing alloy that contain tin, solder I have mentioned, bronzes, that is how actually the ancient human civilizations began, copper, tin, bronzes, which are strong, which are corrosion resistant, and there was a time when bronze was superior to steel in terms of hardness and many properties. Why steel became more popular? Because you could produce a lot of steel far more economically. Otherwise, there are many applications where bronze can be as good as steel, if not better. So, the bronze has also many applications. Bronze sculpture we see, there are many objects made of bronze. Typed metals, in the type sets, the letters are made of bronze because it is very hard. That type thing has to undergo a repeated contact with the surface on which you have to imprint using the ink the letters. It is made of bronze. Then there are other alloys, I need not mention them all. Then there are tin compounds that are used in organic lubricating oil, tin compounds are used. There are inorganic enamels where tin compounds are used, but it finds perhaps maximum use as coating on some other metal surface. This coating can be done in many ways. There can be chemical precipitation on a metal surface. It can be electrodeposited on an alloy, as an alloy or as tin. As a coating, it can be sprayed, there can be decorative coatings, or it can be simply done by hot dipping, that you have a liquid pool of tin and you put whatever you want to coat in that liquid pool, and there we can put a coating of tin alloy or pure tin. So, there are remarkable number of applications of tin. Yet, perhaps the most famous application is tin coating on iron cans, which, as I mentioned earlier, has made us call cans tins. Interestingly, the amount of tin on a coated can is actually very small. It is only about 1.4% of the weight of the can is tin, and its thickness is as small as 0.0005 to 0.00025. So, imagine how thin that coating is, tin coating is, and it is extremely effective. It is impervious, it makes the can inside at least corrosion resistant, and it prevents degeneration of the beverage or food material contained inside. We are going to discuss the extraction of this material with such versatile uses, and we will see it is a fantastic example of pyrometallurgical smelting and refining, and also of chemistry. and it has evolved over centuries. So, many of the steps have been beautifully standardized by alchemists long ago, or chemists if you can call them long ago. Some of them principles are very easily understood. Some one might have to think a little bit as to why there is a step like that. Now, let us talk about its sources. The one main source of tin is cassiterite, which is SnO2. Now, there are not lumps of cassiterite found in nature, but cassiterite in combination of many other oxides and gangue materials. That is how cassiterite is found in nature. There are some countries like Bolivia, Malaysia and Indonesia which are very rich in tin deposits. So, they make a lot of money making tin, exporting and making tin. Unfortunately, in India there are not many known deposits of tin. There is a little deposit in Madhya Pradesh, and some attempts have been made to develop flow sheets for extraction of tin from that cassiterite that is available in Madhya Pradesh. There may be deposit elsewhere we do not know about, but chances are that this country does not have deposits of tin. It is quite possible we have not explored all forests and all remote areas, but as of known data we do not have tin in our country. That does not mean that we should not learn extraction of tin. Nobody prevents us from importing tin ores and producing tin, add value and produce the metal. So, if we have the technical expertise, we can have these processes operating in our country. So, it is necessary we learn about extraction of tin, not only because it is an important metal, but because also it is a very good example of pyrometallurgical smelting and refining. Now, it is not very difficult to reduce SnO2 by carbon, but there is a problem in trying to do that. The problem is tin ores also contain iron. So, if you try to reduce tin ores far too much, then iron would also get reduced and we will not produce tin metal, but iron tin alloy, and they form many things which I will show you little later. So, how do we proceed? There is another problem that SnO2 quite easily dissolves in the slag. Now, we take advantage of that also, and how we proceed is the following. Tin dioxide will not be reduced by carbon in one go. The idea is that we will do that in stages. Why we will do that in stages? Let me explain. What we do that in the smelting at 1200 to 1300 with carbon, we first try to take out some amount of tin. Iron is also coming. We do not want to take too much of tin out of it, because if we want to take too much of tin out, then too much of iron will also come out. So, the aim is to have tin dioxide reduction incomplete in the first stage and produce a metal with 5% iron. But in that process, we have to let go a lot of tin oxide in the slag, does not matter. We will collect the slag and smelt it again with carbon to produce a tin which will now have more iron. In the third stage, again we will take the slag and smelt it, there the tin recovery would be rather small. Now, the first slag that will come will have silica 35%, calcium oxide 30%, FeO 15% and SnO2 as much as 30%. So, a lot of cassiterite that we want to reduce, we do not deliberately reduce, we let it pass off into the slag in the first stage, because we want to produce the first tin which would not have too much of iron. So, that is why this slag needs resmelting for tin recovery. Now, when we get this impure tin, it is not only iron that is there, it contains many other elements and most of them form intermediate metallic compounds like Ca3C, Sn, Sn3 Ag2, FeAs, Fe2s, etc., etc. So, the impurities in tin will be in the form of various compounds. No matter how we produce the tin, we will have to now have a elaborate refining step, where we will need to remove all the elements, impurity elements one by one. We will see how we do that. Here is the flow sheet. We will have a tin ore concentrate. How we are going to produce this concentrate, I am not discussing. But please note that SnO2 cassiterite is a fairly heavy oxide. You know, silica, gangue, etc., density of about 2. SnO2 has a density more than 7. So, we can employ gravity separation techniques, and there are all kinds of gravity separation techniques which exploit the differences in density, particle size and shape. It is possible to produce a fairly rich tin ore concentrate which would have very high percentages of SnO2, not pure SnO2, there will be other gangue materials also. Then we smelt say at 1300 degrees for 8 to 10 hours, we put coal, we add limestone to make a slag, because the limestone will combine with gangue and which would have SiO2, produce a fluid slag. In that fluid slag 30% SnO2 will dissolve. If you want, we can reduce it. If you make it more reducing condition, if you add more carbon, if you allow more time, tin will come out, but iron will also come out. We do not want that. Initially, we allow an incomplete smelting precisely because we want the first metal to be as pure as possible, and we might get as much as 99% tin in that step with only 1% of impurities, slightly different from what I had mentioned a bit earlier. Then this slag is not something that we are discarding, it becomes our raw material. This slag will be cooled, crushed, again smelted, and in this smelting process we will again add coke, again we would have limestone and we would have lot of scrap iron. Why we will add scrap iron? Because iron will dissolve tin and it will help in the reduction process. Aim now is not to produce tin, but to recover tin, and tin will be dissolved in iron. So, in the next process we are producing a second slag which would have only 4% tin as against 30% tin here, and we produce a rough metal which will have 95% tin as against initially 99% tin. The second slag would again be cooled, crushed, it goes through a third smelting operation. All these smelting operations will be in the reverberatory furnace. I have shown pictures of this reverberatory furnace earlier. I will show it again when I start discussing copper metallurgy. So, we go through a third step, again add coke, limestone, scrap iron. In the third step, what is produced is only 80% tin and 20% iron, because you have added iron to dissolve tin. We will get a third slag. This slag now can be discarded, because it is only 1 to 2% tin. We can let that go. So, you see how complicated the process becomes. The idea is to recover tin, also recover three kinds of tin, one which is fairly pure, next step less pure, third step not at all pure, but on the whole we have recovered almost 99% of the tin in the charge. Now, this rough metal, which is 95% tin, we mix with this third smelting metal, which is 80% tin and 20% iron, and it will go for liquation drossing. What is liquation drossing? When I was discussing general principles of refining, I happened to mention a process called liquation. Now, let me give you a specific example as is applied for tin. The process of liquation makes use of the phase diagram. I hope you are able to see this phase diagram here. If not, it is in my book in Extraction of Non-Ferrous Metals when I am discussing tin, but let me say what it says. You know, this is a phase diagram for tin. You have iron on this side, pure iron, tin on this side. You see how complicated this phase diagram is. All kinds of phases are forming. There are also somewhere around 75% tin FeSN, there is an intermetallic compound. There is also FeSN2 intermetallic compound. But the point to note is this, that if we have an alloy which has iron and tin, if you can hold it around 600 degrees or so, then it will separate into two phases. One phase will be almost pure tin, other will be iron with some amount of tin. This is what is done by liquation, that you simply take that alloy which contains iron and tin, take it to a temperature about 600 or so, and it will have two layers now. Tin will float up because it is lighter than iron tin alloy. That iron tin alloy has only a small amount of tin, but what is floating up is almost pure tin, that can be taken out. So, this is the principles of liquation. That is what will be done in liquation drossing. Liquation drossing means constantly you get something floating up and you remove it. Now, this will give us rough dross, second run metal, first run metal, means various stages. This will go for another liquation. The rough dross that has tin, iron, etc., will go back recirculated for total tin recovery. The first run metal, the first layer that will come out will be very pure tin, 99.5% tin. But as you take out pure tin, you are changing the composition of the of what you are purifying. In the second step, it will not be so pure tin. In the third step, it will not be very pure. It will only have 65% tin. It will have 25% iron and copper and lead. This will have to be recirculated back here. So, this is a classic metallurgy of tin, where things are very interconnected. But now, equally interesting is how you purify that impure tin that you have produced. I will spend a little bit of time on that. Now, this you should understand, if impure tin is cooled to just above the melting point, then many intermediate intermetallic compounds that exist as impurities will separate out and float as solid crystals. Tin melts only at 232 degrees. So, we take the impure tin to slightly above the melting point. You have now molten mass. Inside the impurities that we have as intermetallic compounds, their melting points are higher. Remember, I have shown them. You see at the bottom of this slide, if you see right at the bottom, you have Ca3SN 670 degrees. You have an intermetallic compound with silver 596, FeAs 1030, Fe2S 919. So, there are these impurities which are very high melting. So, when there is a bulk of molten impure tin, impurities inside are not melting. So, they will float up. And there are some age old techniques to help these crystals float up. It is done by adding charcoal, because if you add charcoal to the bath, the charcoal is a very light material, charcoal particles will float, and in that process they will carry those impurity intermetallic compounds to the surface also. These things have been evolved thousands of years ago, more than centuries, 2000 years ago. Somebody has found how to do these techniques. So, you go just above the melting point, intermetallic compounds separate out, float as crystals. Now, pulverized coal facilitates liquefaction. Light rising coal particles carrying the crystals with them. Coal also ensures maintaining a reducing condition. So, the impure metal you are trying to purify will not get oxidized. So, there is a reducing condition. Now, if you go, as I mentioned bit earlier, to slightly above higher temperature of 550 degrees, in presence of coal, 99.8% of iron from tin will get separated by liquefaction, thanks to the phase diagram. There is a complete separation of pure tin and iron containing small amounts of tin. That is how the phase diagram tells us. The dross contains 25% tin. Of course, it depends on the temperature at which operating. If you are doing liquefaction at 550, you will get pure tin and you will get iron tin alloy containing 25% tin. Then we can remove copper by adding sulfur. We can add aluminum to reduce arsenic, aluminum arsenide. Also, we can include antimony impurities by adding aluminum, and see the impurity, the melting point is 1720 degrees. They will come out as crystals. 1720 degrees for this and 1070 degrees for this. So, if we add aluminum powder, we will form insoluble skins that contain these solids. Then this comes pure chemistry. In that impure tin, we can add ammonium chloride to remove surplus aluminum that we have added. We may have added too much of aluminum. Aluminum reacts with ammonium chloride to produce AlCl3 vapor, ammonia and hydrogen. They are all gases. Any SnCl2 formed is treated by lead. If during this process of treatment with ammonium chloride it produce SnCl2, then by adding lead we can recover tin, lead will form into lead chloride. These are all chemistry, chemical steps. I will give you a flow sheet, but you must understand how the flow sheet has evolved. One will add to impure tin calcium and magnesium to remove bismuth as a bismuth magnesium compound, bismuth calcium compound. There are two of them, and since you are adding excess calcium, you may add excess. So, that excess calcium will be removed again by adding ammonium chloride. So, the impure tin has to undergo all this, so that we can finally produce pure tin. These are various steps, and there is a flow sheet that should make it bit clearer. This is the flow sheet. We want to purify impure tin. How would you remove iron? Well, remove by liquation around 550 degrees. Pulverized coal will be added. Then there will be a skin formed, skimmings will be separated out. We will add sulfur, that will remove copper, remaining iron. These will all be skinnings, these will all be solids that will come out and removed. We will add aluminum, skimmings would have arsenic and antimony, ammonium chloride for removal of excess aluminum, skimmings. All these skimmings will go again for tin recovery, because they will all have some entrapped tin. We will have essentials for recovery of removing lead. The skimming will have lead tin alloy, that will also go for recovery steps. Then we can add SnCa alloy Mg to remove bismuth, skimmings go for bismuth recovery, again ammonium chloride goes for tin recovery, etc., etc. Finally, we get fire refined tin. Now, these are chemical reactions that have been perfected over a long time, and that is how tin is produced. The interesting thing to remember here is that although it looks very easy that SnO2, why can't you reduce simply by carbon? That would have been possible if you could produce absolutely pure SnO2. It is not that you cannot do that, but it is not worth all the trouble. The best is to have the concentrate, do exactly as has been indicated, so that initially you let go some tin in the slag, produce fairly fine pure tin, second step, third step, then all kinds of steps that have been indicated. So, this is how we produce tin. Let me now go to one or two other elements, and this will be in connection with production of ferroalloys. Now, I have told you quite some time ago that ferroalloys are alloys that contain iron and some ferroalloying element, and these are the examples of ferroalloying elements that are extensively required in today's world in the industry: ferrochrome, ferromanganese, ferrovanadium, ferrotungsten, ferrotitanium, ferromolybdenum, ferroboron, ferrozirconium, ferrochromium manganese. Most of these ferroalloys are used for adding these elements into steel. These are called ferroalloying elements, and it is much easier to add them into steel in the form of ferroalloys firstly. Secondly, it is easier to produce these ferroalloys than these elements in elemental form. If we need them in elemental form, then of course, we have to produce, and there are times when we need chromium as a metal, pure metal, manganese as a pure metal, or vanadium as a pure metal. Then there are methods to produce. So, I will mix up this, that sometimes how we produce elemental thing and sometimes as in the form of ferroalloys. Now, let me first talk about the ferroalloys, one or two general things. In theory, and I am again repeat something that I have mentioned many times earlier. In theory, you can reduce any oxide by aluminum or calcium, which form very, very stable oxides, aluminothermic reduction or calciothermic reduction. In theory, all oxides can be reduced by carbon, because as temperature increases, oxides becomes unstable, but CO becomes very stable. But for carbon reduction, the problem is you may end up not with the metal, but a combination of metal and metal carbide. If you reduce the oxide by a metal such as aluminum or calcium, then there is no question of having a carbon in the metal that you produce. There is another advantage of metallothermic reaction, that is, metallothermic reactions are often highly exothermic. Once initiated, the charge may not need any more heating, whereas carbothermic reductions are endothermic. You have to supply heat for carbon reduction. So, there are advantages and disadvantages either way. Carbon reduction will be something simpler. Carbon is a cheap reducing agent, but it will need energy, it will need a carbide in the metal, but then we can think of a refining step that will produce a metal which has carbon, but refine it and get the pure ferroalloy, or go for calcium or aluminum reduction and produce ferroalloy which does not have carbon. Now, here I have indicated that this carbothermic process is largely employed, it should be here actually, for no, it is okay, ferrochrome production, ferromanganese production, ferrovanadium, ferrotungsten, ferrotitanium, ferromolybdenum. This will not work for the boron, zirconium or FeCrMn, whereas aluminothermic process, means reduction by aluminum, can be employed in all the cases. It can be universally applied, and there are two. There is one example, ferroboron exclusively employed, it is only by aluminothermic reduction, whereas in other cases either there are many places where it is carbon reduction, subsequent refining, or aluminothermic or calciothermic reduction, both processes are employed. Okay. Again to repeat, why do we produce ferroalloys? The reason is ferroalloys are easier to produce than ferroalloying elements, usually used for alloying iron, where a ferroalloy dissolves more easily. Sometimes we need them in elemental form. Suppose we want to talk about production of a ferroalloying element in elemental form. We can take as an example chromium. There will be a method for producing chromium metal. The source is chromite, which is FeOCr2O3, or you can write it as FeCr2O4 with varying amounts of Fe2O3 and Al2O3 replacing Cr2O3. The grades can vary. India has very good reserves of chromite, almost 80% of that is in Orissa. Chromites are very easily upgraded, because one can selectively pick up pieces and one can tell which are rich in chromite. They can be upgraded by flotation, they can be that will be where the gangue is floated up, they can be also upgraded by magnetic separation. Now, we will come to ferrochrome production later on. Let us see how it goes for elemental production of element. For to produce pure chromium, A standard technique is to go through a rotary kiln reaction of sodium carbon into Cr2O3 to form leachable sodium chromate, sodium dichromate. This reaction takes place in a rotary kiln 800 to 1000 degrees. Then once that is leached, you have Na2Cr2O7 in solution. By sulfuric acid treatment, we can precipitate Na2Cr2O7. This is how we do that. 2Na2CrO4 plus H2SO4 will precipitate Na2Cr2O7. This will be in solution. Now, once you get a precipitate, which is a very pure compound of chromium, chromium can then be produced in many ways. It can be made to react with sulfur to produce Cr2O3 pure in this form. Then we go for aluminothermic reduction, produce pure chromium, or Cr2O3 can be dissolved in a suitable electrolyte, and we can go for electrolysis. Actually, for production of any of these ferroalloying elements in elemental form, we have to start with the pure oxide. But let us go back to discussing ferroalloys as we started. I think there is some confusion here. Excuse me. Okay, let's come here. Okay. So, we were here and I have mentioned that aluminothermic process seems to be applicable universally, whereas carbothermic process would be largely employed for some, but not exclusively employed. Now, let us do a bit of thermodynamic analysis. Suppose we have a metal oxide MxOY, this is O, and we want to reduce by carbon. You know, depending on the temperature, either you produce CO or CO2. Let us assume that we are going to fairly high temperatures, because they are stable oxides, these ferroalloying elements form stable oxides. So, we will produce CO, carbon giving you CO. It can also produce metal carbide. MxOY reduced by carbon produces metal, or MxOY reduced by carbon can also produce MxCy. So, we have to see which reaction is going to predominate. Now, in general, the delta G naught values of these reactions indicate that it is not possible to produce low carbon ferroalloy when reducing agent is carbon, because stable carbides are also produced. It will not be all carbide, it will not be all metal, will produce metal with substantial amounts of carbides. So, carbon reduction would always do that. You should know that even in the case of production of pig iron in the blast furnace, what we get is not pure iron, it has carbon in it, up to 4% of carbon in iron, Fe3C in iron. That is what makes it pig iron, it is not pure iron. So, in the case of iron also it forms carbide. So, all these metals produce carbide. But let us look at aluminothermic reduction and do an analysis of this reaction, look at it from the point of view of heat. Let us consider reduction of manganese oxide by aluminum. Now, manganese oxide is found in many forms. It can be MnO, it can be Mn3O4, it can be Mn2O3, it can be MnO2. I would like to ask this question, that which of these oxides will be ideally suitable for aluminothermic reduction. This is the question we are asking. We have a problem. Okay. Now, I have mentioned that aluminothermic reduction is exothermic. So, I would like to do a heat balance to find out how much of heat is available for aluminothermic reduction for each of these oxides, and then find out which will be just right for production of that metal by aluminothermic reduction. Consider the formation reaction of MnO, Mn plus half O2. The enthalpy change is this much, and I have long ago I have said that this standard enthalpy change does not change very much with temperature, almost at all temperatures remain the same, minus 92,000 calories. For this reaction, it is more, they are both exothermic, but the sign is minus. For Mn2O3, we have another figure. For MnO2, we have also another figure. The free energy of formation of aluminum is written like this. For 1 mole of O2, 3/2 mole of O2, it is minus 400,000 calories. Now, one needs at around 2000 degrees for efficient slag metal separation. We have to find how much heat do we need for clear separation between metal and slag. We have to heat the manganese metal from room temperature to 2000 degrees. For that, the data is this much, you can get from the specific heat and melting points and the enthalpy of melting. For Al2O3, the heat required to heat from room temperature, this is this. Basically, what we are saying, we assume the reaction is taking place at this temperature, then we are taking the products at high temperature. So, we need extra heat supply, so that we get a clear separation between metal and slag. Now, we will analyze the heat requirements for different oxides. Reduction of MnO. We can write 3Mn plus 3/2 O2, 3MnO. Enthalpy change is this, because in terms of MnO it was only 92, multiply by 3. For aluminum oxide formation, it is aluminum, it is this. So, if you subtract this from that, we get for this reaction 3MnO plus 2L, Al2O3 plus 3M, the delta H naught value to be like this. So, this is the amount of heat available with us if this is the reaction that takes place. Whereas, how much of heat? We actually would need, we will find that out. Okay. Now, the heat available is this much. Now, heat required to increase the temperature of reaction products, namely L2O3 and Mn, from room temperature to 23 degrees K, because that is where the final temperature we are aiming at for clear slag metal separation would be, we can find out from here. This into this is the amount of heat that we really need. So, this is the amount of heat that is being made available by the reaction, but manganese and Al2O3, if you look at the amount of heat that will require for them to be heated from room temperature to 2000 degrees is this much. So, there is a deficiency of heat, means we need this much amount of heat to take the products up to 2300 K, but the reaction is giving us only this much of heat. So, there is a deficiency of heat. So, if we want to produce manganese by aluminothermic reduction of MnO, then we need to supply heat externally, otherwise the reaction will not be spontaneous. Okay. We can do similar calculations and do the heat balance for aluminothermic reduction of manganese oxides, and we will find that heat available and heat required, if we compare, for MnO being reduced by aluminum, heat required would be 1457 to take the products to 2000 degrees. Heat available by the reaction is only 125. For Mn3O4, heat required is less because of the enthalpy considerations, heat available is more. If we take MnO2, the heat available is much more than what is required to take the products to 121 degrees, and it all depends on the Mn aluminum ratio in the reduction charge. So, the conclusion of this kind of analysis will be that it will be very risky to take MnO2 and try to reduce it by aluminum to produce manganese, because there will be excessive heat and it can be explosive. Of course, when the charge is becoming too hot, it can be controlled also by adding iron chips. We can put iron chips to dissolve manganese and also take that heat to get heated up from room temperature to that temperature. So, we can produce ferromanganese that way, control the reaction. So, we are reducing MnO2 by aluminum, we find there is too much of excess heat, we add iron chips which will absorb the heat, produce ferromanganese, will not allow an explosive reactions. On the other hand, when heat is short, like in this case heat available is less than heat required, we can help the charge by what we call a booster reaction. Like if we add some sodium nitrate or potassium chlorate, they will get reduced by aluminum exothermically, and there is no harm done, because what will remain KCl, it will go into the slag and it will heat up the charge. So, in the industry, if you want to apply aluminothermic reduction for production of a metal from its oxide, all these kind of heat balance calculations are done to see what is the right kind of charge. If there is an excess heat, it has to be absorbed. It can be absorbed by adding iron if you do not mind producing a ferromanganese, or else if you do not want ferromanganese, you want manganese, then you add some manganese you already had, cold manganese, which will absorb and mix with the manganese that you are producing. So, there it will be a diluent, it is a diluent. On the other hand, if you find the heat available is less than heat you require, then you have to put in booster reactions, add chemicals like sodium nitrate, potassium chlorate, which will get reduced by aluminum exothermically. Now, in all these cases, when you are using aluminum as a reducing agent, the alloy produced may contain aluminum. So, we have to worry about that as to what we do if it contains aluminum. I will not discuss this now. There are ways and means of ensuring that this does not happen, or if it happens, how to get rid of the aluminum. But I will stop it here now, and I will continue next time with ferroalloys. Thank you very much.